through it once and we have C16. Twice, 14. 3 times, 4, 5, 6, 7, okay, 8, 2. So after 8 times, so after 8 cycles, we've made 8 acetyl-CoAs there, and we're left with, after the 8th cycle, this is also an acetyl-CoA. So in the end, we get a total of 9 acetyl-CoAs out of that. Each of those, for 8 of them, right, we did this 8 times, so that's 8 FADH2s and 8 NADHs. But because we had 9 acetyl-CoAs, we did this 9 times, right? Because we're left with 1 acetyl-CoA in that spot. So that's 1, 2, 3 times 9. That's 27 more moles of NADH per mole of stearate. And 9 more moles of FADH2. And oh, by the way, that GTP, what's our enzyme? What's our important enzyme there that converts the GTP into ATP? Nucleoside diphosphate kinase. We're also going to get 8 more ATPs from substrate level phosphorylation activities.
Why is it 8 and not 9?
Because oh, you're right, it is 9. But we did that 9 times. 9 more ATPs. Woo! Thank you for catching me on that. Right? And so that's a total of 35 moles of NADH and 17 moles of FADH2. Let's see. If we multiply, what's our normal ratio? 2.5 ATPs per NADH times 35, right? 35 NADHs, that's 70,
like 87?
87 and a half. So that's 87.5 moles of ATP from the NADH, and 17, we get about 1.5 moles of ATP per mole of FADH2. So what's that? Oh, times 17, that's 17 and 8 and a half is 25 and a half. So 25 and a half moles of ATP from that. I hope Molly's having fun following this mess. Plus, oh, by the way, the 9 we made directly. So for a mole of stearoyl-CoA going into the mitochondrion for fatty acid oxidation, we get 87.5 and 25.5 is 113. Did I get that right? Plus 9 is 122. So a total of 122 moles of ATP potentially for each mole of stearoyl-CoA going into the mitochondrion. Now, that is 18 carbons. So if we're going to be fair, if we do 18 carbons, I'm going to move over here, mess up our camera person. If we put 18 carbons worth of carbohydrate in, that would be 3 glucose equivalents, right? So let's see. If we take those 3 glucose equivalents through glycolysis, that would give us 6 moles of ATP, right? 2 in, 4 out, net, 2 each, that's 6. But that would give us 6 moles of pyruvate, right? Pyruvate dehydrogenase, we would lose 6 carbon dioxides and get 6 NADHs from that to get 6 acetyl-CoA, right? And those 6 acetyl-CoA would go through the citric acid cycle with the same ratio. Let's see. What would that be? 1, 2, 3 NADH. So 6 times 3 NADH is 18. And 6 times 1 FADH2. Plus 6 GTPs to 6 ATPs directly by the succinate thiokinase reaction. So let's see. So that's good. We got 6. This NADH, oh yeah, if we're doing this, we also got 3 NADHs there. We forgot the NADH if we're under aerobic conditions. You can't ignore that. But those NADH equivalents, how do those electrons get into the mitochondria?
Oxaloacetate and malate. When it
No, how do they get in there? Suddenly they get very quiet. I know some of you asked me about this before the last test.
Do they?
Isn't the
Huh?
FD?
They don't, do they?
Well, they don't directly, what?
The FD.
The
It
FAD,
transfers it to an FAD.
the glycerol phosphate shuttle. So those actually enter as 3 FADH2s because of the glycerol phosphate shuttle. Right? So, if we take this times our 1.5 ATP per FADH2 ratio, that's 4.5, right? If this is in the, all this is in the mitochondrion, so that's our 2.5 per ATPs per NADH. So that's going to be 15. That's going to be times 2.5. That's going to be 18 times 2.5 is 36, and 9 is 45. 6 times 1.5 is 9. And plus 6. So we end up with 4.5, and 6 is 10.5, and 15 is 25.5, and 45 is 70.5, 79.5, 85.5. Right? Did I get that right? Did you catch all that for a moment? At least get a picture of it. It's all on there? Okay? So, same number of carbons, approximately almost 50% more, 40% more ATP.
So this is just a totally simple process.
Right. I mean, this is how much energy can we get if we put in 18 carbons from glucose. This is how much energy can we get if we put in 18 carbons from stearate.
Is that just because it doesn't cost us anything to go through this process? Where like we're having to invest ATP over here?
No, it's not that. Remember back in the dark ages, I asked you to do the oxidation numbers of these things? If we go through, here, I'm gonna get this out of the way for a second. Yeah, if we look at this, if you take stearate, which is C18H, you take stearic acid, you get, let's see, 18 times 2 is 36. It's got 1 degree of unsaturation, so it would stay at 36, right? If we take the same 3 glucoses, that's 18, and C18, H12 times 3, H36, O18. So what's the oxidation number of carbon in each case? So we've got 18 carbons plus 36 times plus 1, which is what hydrogen is in the compound, plus 2 times -2, which is oxygen, all equals 0. Right? And on this one, you've got the same 18 carbons. We got the same 36 hydrogens, which sound wrong. Gotta be. Okay. And we've got 18. Right? So what does the oxidation number of carbon end up being in, well, let's start with glucose.
0.
What does it end up being?
0.
0, yeah. Carbon ends up with an oxidation number of 0 in glucose. So the carbon in glucose has the same oxidation state as the carbon in the graphite of your pencil. Right? Same oxidation state. What's the oxidation number of the carbon in the stearic acid?
Close to 2.
Yeah, like 1 point something. No, we don't have a keeper of the great calculator or great phone that would act as a calculator. It's like 1 point. 1.78. Right? Right? Plus 1.78. No, minus 1.78. Right? Minus 1.78. So the carbon is starting off much more reduced. And remember, what's the end point of that carbon in either case? Caleb? Where's that carbon?
You oxidize it, don't you?
To what? What's the end product?
Carbon dioxide.
Carbon dioxide. And what's the oxidation number of carbon in carbon dioxide?
+4.
Plus 4. So with glucose, we've only got the potential energy we can extract going from 0 to plus 4. With fatty acids, we've got the amount of energy we can extract going from almost -2 to plus 4. And conveniently, I mean, there are other considerations, but that difference in ratio of the oxidation number changes is pretty darn close to the difference in the ratio of the amount of ATP we can extract from the processes. Right? We're going almost, it's 6 versus 4 here. Right? That's a little less than half again more. Works out. We're out of time. That went fast.